All right, in this podcast, we're going to talk about a special case, a special type of mechanism, um, and how we would write the rate law from that. So here you see you have a three-step mechanism. Notice that the first step is an equilibrium step. That's what those double arrows mean. So it's a reversible reaction. It's a fast reaction. The second step is slow, and then the third step is fast. So the second step is going to be our rate determining step. The problem is the second step contains T in the reactants, and as you can see up here, T is an intermediate. Intermediates cannot appear in the rate law. All right, so this podcast is officially going to be how to write the rate law when you have a mechanism that has an elementary equilibrium step that precedes the slow step. That's a mouthful, right? Okay, so this is the step-by-step way that you need to do this. Essentially, you're going to write the rate law for the slow step. Then you're going to set the equilibrium step, you're going to write the rate law for both the forward and reverse reaction. You're going to set them equal to each other, and you're going to solve for the intermediate. And then you're going to plug that into the rate law of the slow step, and that will give you your true rate law. All right, so I know that was all a bunch of what, so let's actually do it. So first we want to write the rate law of the slow step. So slow step, stoichiometry of the slow step. So it's going to be, rate equal K, and then Q to the first power, T to the first power. Okay, so that's our first step. But here, as I said a while ago, T can't be in the rate law. So the rate law for these two is going to be just straight P is equal to T, right? Okay, so now what we do is we plug this back in up here, and we get the true rate law as rate equal K, Q to the first, P to the second. Okay, hopefully I didn't lose you on this step. All I did was write the rate law for that. I left out rate equal K. Okay, so these are both just first order. And I know that's going to be set equal to the reverse reaction, where this is the reactants, and that'll be just that to the first order. Rate and K are going to cancel each other out here, and then we're going to set these two equal to each other. So let's look at another example. Okay, in this one, you see that second step, writing our rate law based off that. So rate equals K, O3 to the first power, O to the first power. Now notice O is an intermediate, so that means that I've got to keep going. So if I write the rate laws for these and set them each equal to each other, I'd have O3 is equal to O2 and O. Okay, now I have to solve for the intermediate, so I divide by that on both sides. All right, so I get O is equal to O3 over O2. Then if I took this and plug it in up here, I end up with my final answer as rate equal K, O3 squared over O2. Okay, so now technically this is a to the negative first order rate law, right? So you really don't typically see things like this, but things like this can happen. Same process though.